Good morning, Dave Alwa here. This is SE3321 and we are doing Lab 9. As always, on the left-hand side of the screen you should see the lab worksheet. On the right-hand side of the screen I'll be displaying the software we're going through. In the Lessons tab on Sakai for week 9, there's a lab data sheet which you can open, and you should see what I've got shown on my screen right here, which is pretty useful. At least it gets us started. Week 9 lab data. Okay, so this is an example of a Nevada chart for warranty data, and what we want to do is convert it to, by hand initially, to what a standard data worksheet would look like for importing into Weibull. And we do this so we can understand the form of the layout of the Nevada chart. There were some issues with this yesterday. Hopefully this will help clear it up. Okay, so I'm going to change these months to January, February, and so on and so forth like that. So it just helps make it clear what's going on. So January, February, and then if I complete this sequence, coming over, it's a little bit clearer to see that I've got dates. The other thing I'm going to do is I'm going to select the entire worksheet. I'm going to center everything just so it's easier to follow what's going. Okay, so items made in January failed by the end of January were 1 out of 100. There was 100 produced. 1 failed the first month, 1 failed the second month, 1 failed the third month, 2 failed the fourth month, 2 failed the fifth month, and 2 failed the sixth month. For the batch that was made in February, 1 failed at the end of its first month, so on and so forth. So the idea, the number of items that have failed at age in the first month is the sum of this diagonal, which is this one plus 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 this one. So adding all those up together gives me the number of items that failed at 1 month. The number of items that failed when they were 2 months old is the second diagonal, and that's equal to this one plus 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 this one, and that sums up to 6. And the number that were failed by the time they were 3 months old is going to be the sum of the third diagonal and so on. 4 months old failed, is the sum of the fourth diagonal, which is this one, equal, so equal, we gotta put equal sign in to start. This one plus, a little trouble typing here today. That one plus that one plus that one plus that one. Okay. What do I do wrong here? Delete. Okay. This equals fourth month. This one plus this one plus this one plus this one. Okay, and then the fifth month. 1, 2, 3, 4, 5. This, I think by this point I remember to type in the equal sign. Okay, and so on and so forth. Well, let's just finish it up. 6 and 7. Failure. Okay, 7th is going to be equal to this plus this, and the 8th is going to be equal to just the 1 in a month on that diagonal there. Okay, now for the items that are suspended, okay, at the end of, there's only one set of items that are 1 month old. Those are things that have been made in August. Of those, 1 failed and out of 100. So it's going to be equal to the 100 we started with minus the one that failed. Means that there's 99 that have, all that we know about is they're more than 1 month old. For the ones that are 2 months old that are suspended, that's going to be equal to the ones made, to the ones made in June minus those that have failed, which is the sum of these two. Okay, 98 suspended. For the ones that are 3 months old, those are the ones made in May. We started with 100 of those, and we have had the sum of these fail. There's 97 suspended there. For the ones that are 4 months old, those are the ones that were made in April, minus the number that have failed, which for them is this number. For the ones that are 5 months old, those are the ones that are made in March, and that equals the number made in March minus the number that have failed in the first 5 months. For those that are 6 months old, those are those that are made in February, and that's equal to the number that were made in February minus those that have failed since February. Come on, mouse. And last but not least, the ones that are 7 month old, those are the ones that were made in January, items made in January, minus those that have failed since then, which are these. Okay, so 11 of them have failed, there's 89 left over, and those 89, all we know is they're going to fail after a month's out. So this is how we go through and do it. It's annoying, it gets very complicated for big data sets, but that's how it's done. And I know people had a little bit of issue with that in class yesterday, so I wanted to go through it again. Let's pause for a moment. What I'd like to do next is take the same set of data entered into Weibull++ as a warranty folio and show how the analysis is done as a warranty folio. Fit the model there, note what the parameters are, and then go back to Excel to do some further calculations. So I'm at the bottom of page 2 on the lab sheet. I've opened Weibull++. I've selected a new repository, and I've got to the opening dialog for project data. What I want is a warranty analysis data sheet, so I've clicked this. Usually start with standard folio. I'm starting with warranty analysis, and I'm clicking OK. And I get a screen that looks like this. There's 2 tabs in. One is the number of sales or items produced each month, and the second is the number of returns. I think 1, 2, 3, 4. Let me just go back to this. I'm going to add another one just to show another warranty sheet. So it comes in with a set of dialog questions I've already answered, so I got it by default. But I want a Nevada chart. I'm starting the time periods in January to match with what we did before. So I'm going to type in January. Just type in January. Jan. All right. 7 time periods is what I wanted because I had 7 months worth of data. Returns are starting in the preceding month, let's say the 1st of February. I'm only going to do, what did I say? It doesn't matter. I'll do 7 of those to show 7 months of data. And for future sales, I have a year's worth of data. This is going to organize the chart. The important thing about getting these periods, this period block correct, is that if I don't have failures and I leave those cells blank, they'll count them as zeros if it's built into the spreadsheet, which can throw things off. So I want to get the size of the data correctly done. The way Relisoft does it is that the items returned at the end of January would count as being a time equals 0, or they broke when they failed. We don't want that. So items that are returned in the month of January, we'll say came in on the 1st of February at 1 month old. That's an assumption we're making. And that makes the form of this a little bit different than what we had before. We've got off diagonals here. We don't have anything on the principal diagonal, unlike we had in Excel. Okay. So here's my worksheet that I asked for. I said we put 100 in service each of these months through July, so I'll just copy that down. And let's go back now and look at the returns. So my pattern was 1, 1, 1, 2, 2, 2. This is made up data, as we said earlier in class. So I'm just going to type it in 1, 1, 1, 2, 2, 2. 1, 1, 1, 2, 2. And you can see that with this, as always with warranty data, getting the data, having the correct data, entering it correctly is a big deal. You know, these toy examples are easy to work with, but the real challenge for doing this in the real world is to actually get the data to work with. Okay, so I've entered my data. It is the same as I did in the worksheet in the first part of this recording in Excel. And now I've got the standard interface over on the right-hand side. I've got my fit a model, plot a model, distribution wizard, quick calculation pad, all the stuff I had before, and I've got my modeling choices. I'm going to fit a 2-parameter Weibull. I use rank regression, which is the same thing as least squares, standard ranking method, Fisher matrix for the bounds, medium ranks, all the standard stuff. And now I'm just going to fit a model to the data. Okay. And what I get for this are parameters for the Weibull. Let's check something here. I'll go back. Parameters for the Weibull, which I can now copy back over to my spreadsheet and use for my calculations. That's good. This brings us to the top of page 5, and now we've got the data. If I wanted to see what it looked like in a standard Weibull sheet, I could click on the Transfer the Life Data to New Folio, just button here. What that's going to do is create a Weibull folio for me, and if I select on that, I can see the data organized as we did with failures and suspensions by time, slightly different order, but the same numbers, the 89, 799. These are all things we did by hand, so it's done for us, which is handy. All right, let's go back. So that's what doing this part here. Let's go back to my warranty data sheet, and now let's go to generated forecast. And what this does is says, starting with returns for the month, we can go out, let's go 6 months worth of returns, and we'll get the number of items that were expected to be returned. So using the model, it predicts what we're going to have. The spreadsheet right now is rounding the results, but let's take the round away, and now we can get the non-rounded numbers for the number of failures by month of production, and there's some for us in the bottom in totals. And I can copy this into another spreadsheet, or use my cost data to try and figure out what my cost of warranty is going to be as a result of that. And so what we have here is what we show in the spreadsheet, same numbers, 11.4, 12.08, so on and so forth. Okay, so I want to go back and take the model parameters here and go back and do this all exactly in Excel. Okay, so we had a beta was 1.3.23 and 37.240. Not quite the values I have listed in the worksheet, but we'll go back and do it. We'll use the values that are in this worksheet just to be consistent with what the worksheet. All right, so I'm going to close out of Weibull. You see me making a little note of what the parameters are. Yeah. Okay, go back to Excel and do some more analysis in Excel to look at model departures. back to Excel. To make things a little bit easier to work with, I'm going to reduce the size of the window to 150. I'm going to take these calculations we did previously, which we don't really need anymore, move them out well off to the side here. And I'm going to copy the format that I have here and place it down here. I'm going to call, that's called observed. This I'm now going to call fitted. I'm going to put the shape and scale parameters that I fit from before into these particular cells. And I'm going to use the ones I have in the lab sheet just for consistency. 1.302, 151 for my shape, and 39.31376 for the scale ones. I don't know why I've got those numbers in the lab worksheet and we had some slightly different, but it doesn't matter for what the mechanics I'm trying to show. So that you can check your work, I'm going to go through and do it this way. All right, then I'm going to call this cell shape. And I'm going to call this cell scale, just to make life easier. Okay. And I'm going to clear out the contents that I have here. Clear contents. Okay, I've also added these little items at the top of the columns that sum the entries in the column. So this is the sum of those cell entries showing the total numbers that were returned in the month of January. And that, when I copied, came down. That's going to be useful here in a little bit. Okay, so how many items do we expect, given this model, to be returned? Basically, it's going to be equal to the number that were produced in that month times the probability of failing in that month. The probability of failing that month is the cumulative distribution function for the next month minus the cumulative distribution function for this month. So it's because the failures go up to and including the right number. So this is going to be Weibull dot distribution for the particular month. And I got a problem because I took the ones out of here, which makes doing this formula a little bit harder. Okay, so I'm going to stop what I'm doing. I'm going to go back and make this a 1 and this a 2. And then I'll be able to use these particular cells numbers to decide how old things are. Same thing here. Delete that, make that a 1, 2, and make these 1s and 2s again. Okay. Now, so again, it's going to be equal to the number that I made in that particular month. Since I'm going to be copying this cell, I want the column to be fixed here, but not the entire cell address, because I want to move this to the right and down. I'm going to want that particular month fixed. So let me just show that. Times, and now I've got my Weibull dot distribution for how old is the items at the end of the month. It's going to be this month minus, okay, and that again is going to be with the row locked, minus the okay, so this is cell C19. So at the beginning of the month, it's 1 minus 1 is how old it's going to be. At the beginning of this month, it's going to be 2 minus 1 will be 1 unit old. 3 minus 1 will be 2 units old. That's how old it is at the beginning. At the end, it's that plus 1. So that's a little complicated calculation, but I'm just going to show it, and then hopefully you'll see what it is again. And I needed to see what the cell number was because it's blocked out here. So this is going to be equal to this, again, locking the particular column, but not, I'm sorry, the row, but not the, locking the column, but not the row. times liable.dist for items that were this minus C19. Okay, and I'm going to want always to pick out of row 18 and out of column C when I'm doing this calculation. Okay, and then the shape and scale in one for the CDF minus the other one, liable.distribution, and this is going to be I'm sorry, it's going to be D18, again locked for that particular row 18. Minus C locked for that particular column 19 plus 1 because it's going to be 1 month older at the end of the month, comma shape, comma scale, comma 1, close parentheses, close parentheses. All right, and apparently I've got a minus sign wrong there someplace. Let's see what we did here. So, oh, it's failures. Okay, so this should be a plus and this should be a minus. I got the order wrong. No worries. Okay. So, I expect to see on average, I'll have 0.83 of a unit fail the first month. I actually got 1. Okay. So, the reason I put those dollar signs in for the addresses is I've set this up now so that if I copy this over, it automatically updates. What did we do wrong here? Oh, okay, so I messed up here in what my address labels are, and I noticed because I'm getting funny numbers here. This is good to watch and see. Okay, so I always want the dates to be this one minus the other one. So I always want to come out of row 18 on the first number, and I want to come out of column C on the second number. So I've got the dollar sign here in the wrong place. Okay, I'm not coming out of column C. That's what the dollar sign means, is when I copy and paste this, the rows will be relative, but the column will be fixed. Okay, so I fixed that, and now when I copy this over, I get the numbers I expected to see. That's good. Okay, and because I've used these relative addresses, I can copy it down and copy this over again. Life is good. I can copy this down and copy it over again to get my right triangular data. And that's why I was messing around with the dollar signs, is because once I've got the formula right in terms of these relative addresses, I'm not having to re-enter it. Debug it, got it to work once. Now I don't have to worry about making typos again or getting the dollar signs in the right, wrong places, etc., etc. Okay, so I filled this down with the expected number that I'm going to see. And because I still have the columns across the top, that tells me what my expected number of returns are going to be by month. 1 versus 8.3, 2 and 2, pretty good fit, 3, 3.4, okay. 5, 4.9, 7, 6.5, 9, 8.2, 11, 10. So pretty good agreement there, and that's what that looks like. Okay, so that gets us down to here to what our fitted values are for the particular observed data. Now if I want to look for a couple of extra months, if I put an 8, a 9, a 10, an 11, and a 12 in here, okay, then all I have to do to see what's going to happen in the future is to take this and copy it over. And now that tells me how many returns I'm predicted to see in those future months, based on my current model. It just extrapolates over, and it was just that fast. I'll make these bold to be consistent. And it's just that fast, and if I want to know what the sums are, again, I just copy the formula over, and I can see what my predicted returns are going to be. And in particular, if I say a cost per return is $10, then I can make my total cost equal to this number times the total number of returns, and I can see what my expected cost of returns were going to be. Okay, going over time for the units that were made in those first 7 months. Pretty clear. Well, pretty clear to me. Hopefully by going through and doing this, it'll work for you as well. All right, let me pause for a moment. Okay, I'm back. What we want to do next is calculate these, look at the model departures and calculate these chances. Okay, so again, I'm going to copy this general form over, copy, and just put it here, Command V, and now I'm going to put this for chi-squared instead. Alright, and I'm going to clear these contents out. But I just want to get the same format, and I will leave these sums here just for right now because I'm going to use that later. And just to make my life easier, I'm going to give myself a little bit extra room here. Okay. So how do I calculate the chi-squared statistic? That's going to be the observed minus the fitted or expected squared over excuse me, the expected number. That's pretty easy to put in as a spreadsheet. Excuse me for a moment. I had a fit of sneezes here. All right, so this is going to be equal to the observed value, which is this cell, this is going to be equal to the observed value minus the fitted value, quantity squared, divided by the fitted or expected value. Okay, so that is a pretty small deviation. So if I copy this over, I get the deviations for that month. And again, to get the diagonals, I come down and copy over. Copy over again, come down. Probably an easier way to do this, but whatever. Actually copy this cell, paste it there, paste it there, paste it there, and paste it there. Another way to do it. Okay, so those are my calculated chi-squared values, and because I had this sum, those are the ones summed across the rows. What I want to do is add a critical value. So let me put a significance level in first. Okay, so I'm going to use a 0.05 or 5% significance level. And now I'm going to put some critical values in. Okay, for the first one, I'm going to use the chi-dot-inverse. And that's the chi-squared dot inverse function. If I could type, this would be help. Okay, and that asks me for a probability, which is, since I want the right-hand tail for being too big, is going to be 1 minus my significance level, and I'm going to lock this down with dollar signs. And then the number of degrees of freedom, which in this case is going to be equal to, I'm going to use these numbers up here, 1. Okay? So that's my 3.84, which is my 95%, or my 5% significance level for a one-sided upper test for chi-squared random variable. Now I can take this and I can copy this over. And since I use the numbers above, I get the chi-squared values for each of the columns, because it's now for 7 entries, 6 entries, 5 entries, 4 entries, which is what it shows. And like we talked about in the class, what we have here is that these values are all much, much, much smaller against that. In fact, if I made this a 0.95, I could see what the critical values were for being too good a fit. And here I can see that I'm not smaller than that one, but for all these other ones, my observed values are smaller than what I would expect to see, much, much smaller. So I can do the one-sided test by changing the significance level. But let's put it to 0.05 like we had in the lab sheet and continue to march. Similarly here, I could put my critical values equal to chi-squared dot inverse. And again, for my probability is 1 minus my significance level. I'm going to put a command T there. And then the number of degrees of freedom again is, in this case, the number of the months of production, and I copy and paste that down, and I can get it for the other way. So now I can compare the totals. These are my critical values, and to compare that against, I would equal out the sum of the rows. And again, if I copy this down, I get similar numbers. Because I'm adding blank cells there, I'm getting these little right triangles in the upper left-hand corner, but it's not to worry me. So in particular, when I've done this, none of this data looks like the number of departures is unusually large. It's all good. Now it's hard to go through and pick these out through our eyes, so what we're going to do is we're going to do some conditional formatting. So in particular, I'm going to take these cells, okay, and I'm going to go up to my conditional formatting. And so for each of these individual cells, I'm going to say if the cell value is greater than this one particular critical value, I want to make the cell equal to red. Okay, and none of them turn out to be red because, oops, I actually did that wrong because I included this last column here. So let me go back to that, to my conditional formatting to manage rules, and let me just delete this rule, or edit this rule. Okay, so instead of being a column K, we'll make it to column J. Okay, one click. Okay. And now what happens if I make one of these observations really big, let's make this one 10, then this value gets to be bigger than the critical value, 3.84, much bigger in this case, and the cell turns red, it's easier to see it. Let's go back and make that a 1, that problem goes away. Similarly for these, I want to add another conditional formatting. So if the cell value is greater than I'm going to take the lock off the column because I want to do it pairwise by the cells. Okay, the values in row 32. Okay, and now if I make this a 10 again, oops. Okay, so now this cell triggers, and also this triggers for the month of returns because the value of the column is bigger than the critical value. And similarly, if I want to do the same thing here, I'll do it on this side. I'm going to format these, conditional formatting. If these cells are bigger than this one, and now I'm locking the row, but not the, I'm locking the column, but not the row. Delete this twice again. cancel conditional formatting, highlight cell rules that's greater than this one, but I'm taking the dollar sign off, click OK. Now this one signals as well. And that's what I've done in the class using the conditional formatting and these rules to show through. And that's pretty handy. That allows me to pick up model departures. So I'll go back and make this a 1, and for example, if I make this a 2, and a 2, and a 3, and a 4, and a 5, let's actually go back and make this a 4. Make it a 3 as well. So I make this a 3. And make this a 4. Okay, so for this batch here in February, I've increased all these numbers. None of the individual months is significantly larger, but the cumulative effect of these upward departures says that there's something going on funny with that particular month. And that's pretty handy. Hold on here. Let me stop. Okay, I'm back. You may have noticed me pausing a bit there at the end of the last segment when I saw a problem. And here's what the problem is currently I have this cell. Currently I have this cell, the degrees of freedom of this cell being equal to the month, C19. But that's not quite right. This is not one set of data, this is 7 sets of data. So what I'm going to do is I'm going to use a different formula here, which is going to be equal to the count of the cells that I have here that have entries in them. Okay, let's see if that works for me. Okay, and now since I've got 7 cells with data in it, this gives me the correct 14 that I had over here. And so I'll copy that formula down and use it that way, and that actually gives me better values. And now this 6 that I have is not significant against this critical value of 12. I would have to make this more like a 5, and maybe this like a 3 to get it to go over the total. Same idea, but that was an important catch here that the I've got to make sure the degrees of freedom here match the number of entries that I have, and I had the indexing done wrong. And so using the actual count function is a lot easier way to do that. Okay, let me go back and give myself the original data. Two. Okay. All right. The last thing I want to talk about is not really in the homework, but it's this idea of calculating the number of returns for a warranty policy. And it's a good reminder that we can use simulation to do a lot of handy things for us. So when I was mentioning in class, sometimes when you return an item, you get a new one, and the warranty on that item can either be for the life of the new item, or it can be for the life of what the original item would be. In other words, if I have something that's warranted for 12 months and I return something at 8 months, the replacement is only going to be warranted for the remaining 4 months of the amount of time that I have. That's called the a replacement policy where limited to the original warranty. So to calculate the cost of that, we'd like to know how many items are expected to fail under that original warranty. So I'm going to just do a little demonstration here. I'm going to do a shape parameter, and I'm going to say that's going to be 1.5, and the scale parameter, I'm going to say that's going to be 2, and this is in years. I'm going to do a warranty period that's equal to half of a year. 0.5. Okay, I'm going to call this cell shape 1, because I already have a cell called shape. I'm going to call this one scale 1. Okay, and I'm going to call this one, what do you think? Let's call it W. Okay, good. All right, so I want to set up some trials here. I have 1, 2, 3. And I want to count the number that are failing under warranty. If I could type. Okay, and I'm going to put wrap text on here so it all fits there. And then I'm going to have a first time and a second time, and I'm going to do 6 of these. Okay. And I'm going to say if I get more than 6 returns under my warranty, I'll just flag that as an unusual case, but I can worry about it. Okay, so what I want to do is I want to calculate some return times, and these again is in years, and I'll just put some sample data in here. Okay, times of failure. So if I have my first phone, think of phones, and it lasts for a year, then it's never going to be returned in the warranty, and the number of fails would be 0. Okay. But if its life was only 1/10 of a year, then it would fail, and I get the second phone, and between the two of them, they'd last 2.1 years, which exceeds the warranty period, so I'd only see one phone being returned. But if this was a 0.1, then this one would fail in 1/10 of a year, this would fail in 1/10 of a year, and so I would have had one return. I'll get the second phone, but it will last, the sum of these is 3.2, which now exceeds the warranty period. So I'm down to 2 have failed under the warranty. Okay, so on and so forth. So I need a way to count these things. And what I'm going to do is I'm going to give myself this formula. I'm going to use a bunch of nested if statements. So in particular, I'm going to say if this first time, and I'm going to lock down the column, but not the row. So put a $sign here. Actually, I don't need to even do that because I'm going to be copying the formula, so that'd be fine. If this is greater than the warranty time, then I'm just going to return 0 because nothing will have failed. And otherwise, then I'm going to do another if. See, this is what I hate when these things start copying the cells. If E54 plus F54 is greater than the warranty time, I'll return that 1 failed. Else if E54 plus F54 plus G54 is greater than the warranty time, then I will have returned 2. And now if E54 plus F54 plus G54 plus H54, if the 4 times are greater than the W, then I will have failed 3 phones. Otherwise, if E54, I'm just going to write sum now, sum of E54 colon, what am I up to, I54 is greater than the warranty time, then I will have had 4 failures. And if the sum of E54 to, what am I up to, J54 is greater than W, then I will have had 5 failures. And if that doesn't work, I'm going to stop, and otherwise I'll return error. Okay, now I got to put some parentheses back in here. I think that's the right number of parentheses. One more, okay. Alright, so now my formula says 2 failed under warranty. Again, you can see it's written out here, a general idea if you want to follow that. But let's just test it. If I make this a 0.1, it says 3 failed under warranty. If I make this a 0.1, 4 failed. If I make this a 0.1, 5 failed. And if I had all 6 phones under warranty, go up to J. Let's see what we got here. I should be getting it 1, 2, 3, 4, 5, 6. Let me see what I got here for this last term. If E54 through J54 is greater than W, oh, okay, I did. Okay, so it's not an error. Let's make this make a 0 here, and make this a 0 here. Okay, then if I've got 6 failure times or less, the sum of them is less than half, then I get an error, and I know that to flag that case. Okay, so the question becomes now, where do I get these times from? So what I'm going to do is I'm going to use the inverse cumulative distribution function for the Weibull distribution and the formula that we talked about, I don't know, week 2 or week 3 for generating these values to generate the random variables. So I'm going to strip these out, and so clear contents here. So I'm going to say that this is going to be equal to my scale parameter times minus the natural log of some random variable, uniform random variable, which is my rand function, raised to the 1 over my shape parameter. And I think that's my number random variable. Well, I guess I'm missing a second one. Alright, so that gives me a failure time of 1.8. I happen to know that the mean of this distribution should be about 1.8, so that's handy. If I hit the F9 key, I can get different draws, and it looks like I've got about the right number of times. Okay? So now if I copy this over, I've got 6 potential lifetimes here, and none of, for these phones, none have failed under warranty. If I hit the F9 key again, I get some different values, and I'm continuing to cycle through. And it's very unusual to pay a warranty claim here. I haven't paid one yet. I've gotten close. Now here I've got one where the first phone only lasted for 47 hundredths of a year, so we ended up paying 1 warranty claim, and so on and so forth. All right, well, what I'd like to do is to run a trial, run 100 of these trials. Okay, 100. I'll just copy this whole thing down, this whole shooting match down 100 times. And now what I would like to do is find the average of these numbers that are failing under warranty. From my 100 trials, my average number failing under warranty is 0.16. Okay, so the cost of warranty is, if I give myself a cost per return, let's make that a C. Okay, $10. Then my cost of warranty MW, which is defined in the book, is equal to the cost of return times the original one I made plus the number of that were average number failed under warranty, and that tells me that my average cost here is 11.4 using equation 17.4. Then if I made that cost equal to 80, then I'm getting a cost of about 17. Sorry, 80. Then I'm getting something similar to what I have in the spreadsheet, and if I hit my F9 key, it recycles and does a random draw all over again, and I can see how much variability I have in that by doing some experimentation. Okay, couple points. This answer doesn't agree with what's in the book in table 17.1, and I went back over and over again and was sure what I did was correct. So I went to the references that Blischke and Berthy referred to where that table came from. There's a link to the 1982 Technometrics article there, and I checked my model against the Technometrics article, and it's right. So the textbook is wrong, and it just is. It is what it is. A couple other things. If I put in this 1 point, make this cell equal to the value I had earlier for my fitted value, and I make this the scale parameter equal to the value I had from before from this scale, equal that one. Okay, this was in months, so if I give myself a 6-month warranty period, now I can see how I'm doing under this new warranty, under that warranty, and can see what my average number of returns would be under that policy. And it's not too bad. But if I make it a 12-month warranty, and hit the F9 key, still not too bad. If I make it a 2-year warranty, now I'm starting to see my average number of returns come up. And if I make it a 4-year warranty, I'm sorry, 48-month warranty, my average number of failures is a 1, and this starts to get very, very expensive. So it allows me to play with the projected cost of these warranty policies doing another way. All right, and the other thing is that, you know, there are errors in textbooks. So, you know, if you've done something and the book is wrong, it could be that it's not your problem, it's the book's problem if you two don't agree. All right, so that summarizes what I want to do for this lab. Again, there won't be any questions on this cost of warranty simulation, but I just wanted to show it. And I think the value at the end of this course is not only do the reliability, but also pull in some simulation ideas, some statistical hypothesis testing ideas, and to pull a lot of different skills together to answer a wide range of questions. So hopefully you feel like you're learning something, and we'll see how the homework goes. Hopefully this helped. Thanks.